Hello, I am Dr. Sheetal Silal from the Modelling and Simulation Hub Africa at the University of Cape Town, and I will be describing the development of a mathematical program called the METCAP model. This video series comprises three parts: an introduction to the METCAP model, developing a Plasmodium falciparum transmission model, and incorporating Plasmodium vivax malaria. The METCAP model is a dynamic epidemiological economic model that has been developed for the 22 countries in the Asia-Pacific region. With significant reductions in cases and deaths in the last decade, several countries are now working towards national elimination, and a regional goal for a malaria-free Asia-Pacific has been endorsed at the highest levels. The purpose of the METCAP model is thus to project the decline in incidence to elimination by 2030 and to determine the costs for elimination in the Asia-Pacific region. So how does one develop an epidemiological economic model? To build an epidemiological model, you first write equations to describe the biological behavior of the parasite in the mosquito and human. You add environmental data such as rainfall and temperature, as these have an impact on malaria transmission. You then incorporate existing population demographic data and health system records to create a computer-generated synthetic population that has features similar to the population of interest. The model testing phase involves predicting the potential impact of proposed interventions against malaria on the computer-generated population and computing the costs of these interventions. This step is repeated several times to account for uncertainty in the epidemiological and cost data. The results are then analyzed to make recommendations. The model development phase of the METCAP model involves developing a transmission model for Plasmodium falciparum malaria and Plasmodium vivax malaria. Let's begin with falciparum malaria. We can divide any population into three distinct classes depicted by the yellow boxes: the non-immune, the infectious, and the immune. The arrows represent how the population shifts between classes. For example, the non-immune may become infected with malaria. The infected may recover naturally and develop immunity to malaria. But this immunity is not permanent and may be lost over time, so that the population is once again non-immune. But not everyone in the population responds to falciparum infections in the same way. Some will have a clinical infection where they will experience malaria symptoms. These infections may worsen to become severe malaria. Some infections will be asymptomatic with a generally lower level of parasites compared to clinical malaria, and other infections will be submicroscopic with a parasite level that cannot be detected by slide microscopy. One can recover from a malaria episode in two ways. Natural recovery can occur with symptomatic infections becoming asymptomatic and eventually curing entirely. The other way to recover is through drug therapy. Treatment can be received through the public health system and through the private sector. Upon being treated, infections will cure to a state where false positive results may be possible on some rapid diagnostic tests due to the presence of the HRP2 antigen. This effect will eventually wear off after a few weeks. Upon being cured from a previous infection, the immune may also be reinfected with a higher probability of developing an asymptomatic infection. With mosquito bites occurring fairly often, it is possible to have more than one malaria infection at the same time. This is called superinfection. Bringing these concepts together, we have a model for Plasmodium falciparum malaria transmission. But the Asia-Pacific has two major malaria species. What about Plasmodium vivax? Incorporating Plasmodium vivax malaria. The model for vivax malaria is not the same as the model for falciparum malaria. With Plasmodium vivax, the presence of hypnozoites and the resultant probability of relapse must be included in the transmission model. Plasmodium vivax malaria infections may recover with and without the presence of hypnozoites in the liver. The presence of hypnozoites may trigger relapses of the same Plasmodium vivax infection weeks, months, or sometimes years after the initial infection. Like falciparum malaria, it is possible to have more than one vivax infection at the same time. But what about a mixed infection? It is also possible to carry Plasmodium falciparum and vivax parasites at the same time. If this is the case, there are several interactions to take into account. Firstly, there is dual treatment, where the population with a mixed infection who are being treated for vivax malaria will also be cured of their falciparum malaria and vice versa. Research suggests that the population who have been treated for a falciparum malaria infection have an increased chance of triggering a relapse of a previous vivax infection compared to the rest of the population. Malaria infections are not always correctly diagnosed. Different brands of rapid diagnostic tests have different targets, and it may be the case that non-falciparum malaria is masked by and hence treated as falciparum malaria. In summary, mathematical models require all these inputs: the biology of the disease, the spatial resolution, environmental factors, health and economic data, in order to combine all these elements in a model to test a set of interventions to predict the costs for and the rates of decline to elimination by 2030 in the Asia-Pacific region.